Okay, I think we got a lot worked out that way. What were we talking about last time? Yeah. Okay. So we're discussing fugacity. And we gave it the symbol fancy F. Okay, what is fugacity? So I want to know like the equation associated with it. And I want to know like what does it mean? Mm-hmm. Yeah. So if we were considering activity, you had the activity coefficient times the concentration. So what does this constant tell you? So what were you saying, Shannon, about this thing, this fugacity constant? Yep, like the activity coefficient. And what does the activity coefficient tell you? Yeah. Yeah. So these tell you how ideal the system is behaving. If this were a completely ideal system, what would the value of the activity coefficient be? Yep, it would be 1. What's a really crummy value? Like let's say a system is not behaving ideal. What will the value of this be? Yeah, low or something else. Okay, and this fugacity coefficient, it's dimensionless, just like the activity coefficient. It has no units associated with it. And I think we derived an expression. Did we get to something like that or no? Okay. Where does this come from? Last time we came up with this expression, right? Right? So what are we going to do to transform this into this? Or what appears to be the only change? Yeah. Oh, I guess I should have been. Sorry. So what's the only other thing that yeah. We're using fugacity instead of what's this thing? Yep, pressure at non-standard conditions, right? So that P naught was for standard conditions. What typically is our pressure at standard conditions? Yeah, 1 bar. So we've modified it that way. Okay, I know I asked and you guys answered some of these questions, but I just want to state it again. So what is fugacity for an ideal gas? So we got fugacity is equal to the fugacity coefficient times the pressure. What would it be for an ideal gas? Yeah, because what's the value of this for an ideal gas? Yep. Okay. What we're going to do next is we're going to build a table to illustrate how fugacity changes as we look at a system. So we're going to consider fugacity of nitrogen gas, and we're going to hold the temperature constant at 273 K. we're going to keep track of the pressure in atmospheres. And the fugacity in atmospheres. So notice, what should the units of fugacity be given this equation? Because what are the units on this thing? Yeah, there aren't any units there, so what should fugacity's units be? Yep, ATM, or whatever the pressure is. Okay, we're going to keep track of the pressure. I'm going to switch colors. Let's go to yellow. 1, 10, 100, and 1,000. Okay, let's consider the fugacity. The fugacity, will they be equal to one another? Is N2 an ideal gas? See some head shakes, no. Why is N2 not a good ideal gas? Or why does it not behave ideally? It's not monoatomic, so that knocks out a lot of ideal behavior, right? Okay, so that's not good. The other thing is if you looked at the variable coefficients, you know that nitrogen has values for those variable coefficients, and they're a lot higher. N2, is it inert? Well, what do you think? If I leave out a nail, what happens to that nail? Like outside? It rusts. What's rusting it? That is oxygen. What's the N2 doing? Jack shit, it's not doing anything. N2 is relatively inert. So it's good in terms of that, but the non-monoatomic situation that we have here makes it non-ideal. So what do you think about the fugacity coefficient? Are these two going to be equal to one another? No. We consider it. Okay. How different are these two numbers? Not very different. What do you think is going to happen as we increase the pressure? Yeah, the difference between them is going to increase. So if we have a pressure at 10, we get 9.9560. At 100, 97.3, and 1,000, 1,090. Okay, what do you notice about these three? I'm sorry, can you say that one more time? Yeah, they're lower than, what about at this pressure? Higher. There's a lot of weird behavior that happens with fugacity. Okay? Really, to determine it, you have to look at something experimental. Oh, we can calculate it too, but you do some experiments based upon those calculations. Okay, so the next question you might be thinking is then, how do we get this thing? That's what we're going to talk about next. So question, how do we get that fugacity coefficient? To do that, we're going to return to an equation we derived a bit earlier. Whoops. What do you guys prefer, V sub M or V bar? Any preference? I like bar too. I don't have to write a little M. Okay. And then we also derived an expression some pressure P right? Okay, we're going to use that. We're going to plug that in here. If we integrate this side, what do we get? Yeah, delta G. Basically, G at some pressure minus G at another pressure we're going to call P prime. And we're going to solve for this in a little bit, but before we do that, let's plug in this expression into here. So what we get is G naught minus RT ln F over P naught minus G prime plus RT ln. We're going to call this fugacity of F prime naught. Like that. Where what is this in relation to the pressures we have? What pressure is this at? Yep. And what pressure is that at? Yeah. Okay. We can simplify this a bit further. We'll do that up here. Yeah, I'll do it right here, whatever. What would you suggest to do there? Yeah, those are going to go away. Any other things to do? Or do we just want to write it out so it's clean so we can see it a bit better? Okay. Okay, so we get that. What would you suggest to do next? Yeah, let's pull out the RT. So that's what we get. Can we make this any simpler? Can you be a little more explicit about those natural logs? Yeah, oh, you want to do it? We can do it that way if you want. I was going to think not expand them, but let's squish them. It's the same thing though, right? Okay, so we get this RT ln Not Ellen. Ellen. It's hard. It's like how I can't say Lily's name ever. So wear braces forever. All right. A weird thing to say. Anyways. What do we got here? What's going to be on top? I'm going to be kind of simple. F divided by what? Yep. And what goes in the denominator? Yep. Divided by what? Yep. Anything? Can we simplify there in any way? Yep. P naughts cancel. Gone, gone. What do we got then as our expression in the ln? Yeah. Okay. Might be going, that doesn't get us our coefficient yet. What the hell, Dr. Simpson? We've been spinning around in circles doing this. So going back to our original equation, what side have we dealt with the entire time? Yeah, we've messed with the left. What could we set that equal to? The right. And that's what we're going to do. V prime, V bar. We said V bar. Yeah, we did. Is equal to that. Okay. This expression, this is for real gases. Let's compare this to an ideal gas. So I'm going to put perfect for a perfect gas. Some people feel like there's a big difference between the two. I'm not going to really complain about that. Okay. RT, what's this going to become for a perfect gas or ideal gas? ln of what? Sorry, what was that? Not. Let's take a step back a little bit. It might be. But we're going to wait a second. So it'd be F over F prime for a real gas, right? Fugacities. What would it be for an ideal gas? Yeah, P. P over P prime. Okay, let's look at this a little bit further. We have a solution to this side. What would you suggest to do here? Yes, PV equals nRT. All right. Okay, what's V bar again? Yep. Okay, what do we want to manipulate this to be then? Yep, so let's push this around. V, what are we going to do with that P? Yep. We're getting closer. What next? Yeah. Okay, what do you suggest to do now? Yep, plug it in to here. So we got the integral P prime. What's our integral going to look like? Yeah. Geez. We can pull out that RT. And what's that going to be equal to? Yeah. And we showed that that's true, right? So we proved it in 2 ways. Okay. Now, what we're going to do next is we're going to compare these 2 equations. So let's compare equations. So when we say a comparison, what do we mean mathematically? What function do we usually do for a comparison? Inequality. Oh yeah, I guess we do that. I was looking more for a subtraction. Inequalities are probably a better way to look at it, though. I want to compare through this subtraction. So we're going to compare the actual VM to the perfect. And then we're going to compare that. We're going to subtract these 2 things from one another. So we got RT ln of what? Yep. Minus what? Yep. Okay, what can we do with this side? Yep, pull out RT, slap the LNs together, and what we're going to get is RT ln and that's equal to this integral. Okay, the next question I'm going to ask you relates to fugacity. What did we notice, like if you look back in your table for N2? What we want is this to be true. When is this true? Low pressure. So if we were to consider a limit, what would we want P prime to approach? We want to approach 0. We can pick any pressure we want. And if we say we go with that one, what happens to the value of this then if we assume all of that? So So pressure is going to start dropping to 0. These two become more equivalent to one another. What would their ratio be? 1. No. Not trying to do any tricky, weird divide by 0 math stuff. So then our expression up here is going to become the following. How does this integral change? What changes with its limits? What were we saying p prime approaches? 0, so what should the lower limit be? Yep. Sorry, should be a p prime. And then we got the difference between these two. Okay. What's fugacity equal to again? Yep, constant times what? B. So how about we take that, we plug that into here. I think we're forgetting something on this. No, not yet. We'll get there. Oh, yeah. So let's take that knowledge. Let's plug this in here. So you got RT, ln. What's this going to be? Yep. Divided by what? Yep. Is equal to what can we change or get rid of in this expression? Yeah. Those p's are going to go away. Hey, we found the activity coefficient, or excuse me, the fugacity coefficient. So now, what could we do here? Because we want to isolate that guy by itself. What would you suggest to do? Yeah. Yeah. Okay, we're not going to exponentiate yet, which is now my new favorite word this semester, because we got to deal with that integral, and it'll be a huge pain in the ass before that. Okay. Let's take a step back. What's that equal to? RT, yep. Divided by what? Mm-hmm. Going way back. How does our actual molar volume compare to the perfect? Or what's that equal to, that ratio? Way, way back. Lab 1 way back. What were you going to say? No, I'll say it. I think you're there. Yes. It's related to the virial coefficient. It's Z. What was Z? It's what is it for an ideal gas? That's 1 for an ideal gas. Do you remember what Z was called? Yeah. Therefore, if we wanted to manipulate this around, whoops. We got this, right? Okay, if we do some more manipulation, we plug stuff in, what we'll eventually find is this equation is true. And we can manipulate this around and exponentiate after we do our integration to figure out that fugacity coefficient. And that's what you guys are going to do for your next daily problem. Sorry, I went over time. How much time did I go over by? 2 minutes? Oh no. Okay. Any questions about this? So a lot of manipulation. We pulled back compressibility away into the catacombs, from the catacombs of your mind, where it is now. You got to do this for the next daily problem. Okay? All right. Have an awesome day.